talk in the afternoon is by Tommaso Maria Botta, who will be talking about the Maulik-Okounkov Lie algebras and the BPS Lie algebras.
Okay, yeah. Thank you very much for the introduction and the opportunity. So today's talk is about the Maulik-Okounkov Lie algebra and the BPS Lie algebra. So as you can guess from the title, there's some representation theory, but hopefully we'll manage to convince you that the algebras appear naturally in enumerative geometry, and so it's worth having a look at them. And of course, I want to say that this is joint work with Ben Davison. So we'll start with some motivation. Okay, so let's assume that we are given a quiver Q. So for me, a quiver is a pair of vertices and edges. So whenever I'm given an edge E, I can consider two maps, the target and the source map, that will give me the corresponding source and target vertex. And so typical examples to have in mind, well, so you can consider, for instance, the A2 quiver. If you like a finely algebras, maybe E3 hat, or if you like loops, Jordan quiver, so things like this. You can take, for instance, an arbitrary linking diagram if you want to study semi-simple Lie algebras. Okay, so what can we do with a quiver? So as already said, given a quiver, I can study the Moduli algebra associated with the quiver. So if Q has no loops, at least. So we'll discuss how to remove this assumption soon, but so for now, let's assume that Q has no loops. So given a quiver without loops, I can study its Moduli algebra. It has some standard triangular decomposition, which is given by some invariant bilinear form. Okay. And so let's say that we want to study such a Lie algebra. So what do we do? So let's say that we want to study from a geometric perspective. Well, there's a natural thing to consider is the space of representations of the quiver. So we can define the space of representations of the quiver Q for some dimension vector D indexed on the vertices of the quiver. This is just a space of Homs, linear Homs from a certain field. We'll specify it soon. So I'm defining the space of representation as a direct sum of Hom spaces depending on the edge. So for instance, for the Jordan quiver, I will only have a Hom space. So this will be some endomorphism space of a vector space. And yeah, so that we can consider an action of GLN here, or more precisely, as many GLN as the vertices of the quiver. So I'll define GD as the product for all I in the vertices of GL DI. And what? Where? Here?
No, one line above the home.
Here?
Yes. A to the GI.
Thanks. Thanks so, yeah. And okay, so but let's say that we want more geometry, we want to consider some more interesting varieties. So then we might want to consider Nakajima quiver varieties. So how to construct a quiver variety? So let's say we start from a quiver Q, and we are given another dimension vectors. let's call it differently. So now we define a frame quiver. So I will give just an example how to define the frame quiver. So let's say we want to consider the frame quiver of A2. So we are given the A2 quiver. We are given a framing vector, so this will be a pair of numbers and non-negative integers. So to define a frame quiver, we add a vertex at infinity. So this is just another vertex, and we add as many arrows as prescribed by these dimensions. So this is, for instance, F2 arrows, and this is F1 arrows. So if we are given such a quiver, then we can consider the free space of representations. And I'm prescribing that the dimension vector of is D1, so I'm putting, let's say, D1 here, D2 here, and 1. And also consider its cotangent bundle. Okay, this is something symplectic. And I want to consider the GAT symplectic reduction with respect to GD. So more explicitly, this is going to be the zero locus of the moment map defined by the Hamiltonian action of GD. And this is just the GAT quotient with respect to some character of GD. And this is by definition the quiver varieties associated with this data. So, what can we say about our Lie algebra if we are given a quiver variety? So there are two important facts. The first one is due to Nakajima. So that the Moduli algebra acts on the sum of the cohomologies of my quiver varieties. So if I want to study a representation theory for my Moduli algebra, I might pick a direct sum of quiver varieties, take its cohomology, and study the action on it. And the second fact, which is comes more from the study of so combinatorics of quiver representation, is that, but also from out of representation theory. So if I pick a specific weight space of weight D of my Moduli algebra, and I consider its dimension, this dimension will be equal to the constant term of the Katz polynomial.
So it's a weight space when it acts on itself. It's the weight space when it acts on itself.
I mean, it's a root space. A root space. Where the Katz polynomial is defined is the number of absolutely indecomposable representations of my quiver, but for the field FQ. So in other words, this is those representation of my quiver over FQ that are also indecomposable for the algebraic closure of the field itself. So, and this is a polynomial with positive coefficients. It's not trivial at all to say this, but that's true. So there are all these interesting facts. These are stories from the last century. But so what can we say nowadays? So we can ask ourselves the following questions. So these questions are those that I will try to address in the talk. So what if we want loops? So far I was studying Moduli algebra, so I was assuming that the quiver has no loops. But what if I want to allow them? So the second question is, what if I want to recover the whole Katz polynomial? So I want some kind of Lie algebra, possibly some kind of extension of my original Lie algebra, whose graded pieces, with respect to some filtration, will recover not only the constant term of the cut polynomial, but the whole of it. So,
Excuse me.
yeah.
So before, the no loops assumption means you could have like cycles.
This is allowed, but this is not. Yeah. So loops based, so one loops, not so. Okay. So question 3. So where is the enumerative geometry? And so there's also a question 4, but before stating it, so let me say that there are a fact. There are 2 candidates. So the first candidate is a called Maulik-Okounkov Lie algebra. And the second one is the BPS Lie algebra. And maybe I should say that this is due to work. So the fact that this Lie algebra exists, we can work with it is due to the work of Davison. And so again by Davison and Nakajima. And should I get my?
So this is the BPS Lie algebra for Calabi-Yau category in general.
Yeah, correct. But yeah, you can relate it to the 3 Calabi-Yau case by some dimensional reduction. We'll get to it soon. So soon I will discuss each of these Lie algebra individually, and I will say more about them. And so the last question is, are these 2 Lie algebras related? Hopefully, I will improve my writing soon. So, okay, this was just the motivation. But okay, we already have many questions to address, so let's start.
So why they are candidates? Do you mean that both have action on the homology?
Yeah, it turns out that they do have such action. I will discuss it soon. So let's start with the Maulik-Okounkov Lie algebra. So how to define this Lie algebra? So let's say that we are given a quiver variety as before. And okay, so I haven't said it yet, but so consider you should whenever you are given a quiver variety, you should keep in mind there's some torus acting on it. So and you can split the torus in the following way. So the C star H bar action is just a one-dimensional torus action that rescales the cotangent directions of the quiver variety, essentially. It comes from the level of the category of the representation of the Lie algebra. And there's also an additional action that, as you see from the notation, it depends on the framing. And it comes to the fact that whenever you're given an arrow here, you can rescale it by some constant, non-zero constant. Okay, and so let's write the following theorem. So, which is by Maulik and Okounkov. So, there exists a Lie algebra, which I will denote as MOQ. MO, of course, stands for Maulik and Okounkov. And this Lie algebra has some triangular decomposition similar to the one that we would expect from a Moduli algebra. Such that the given line bundle in my Picard group, then the quantum multiplication by the first Chern class of this line bundle so here I simply want to stress that this is quantum multiplication, so in the sense of Gromov-Witten theory, is some, of course, it's some deformation of the classical multiplication by cap product, but the deformation is governed by this Lie algebra. So I will write in the following way. So what are these two guys here? So you should think of this as an element of the universal enveloping algebra of this Moduli algebra. So essentially these are dual basis elements. So let's say that alpha q, alpha d is in the root d piece of the Maulik-Okounkov Lie algebra, and alpha minus d is the dual with respect to some bilinear pairing that defines the splitting. So I don't want to be more precise, but I would simply want to stress that the quantum multiplication is determined by this Lie algebra. And actually, one can say more. So actually, this Maulik-Okounkov Lie algebra lives inside some larger algebra called the Maulik-Okounkov Yangian. This is some sort of, this is a Yangian. So it's a rational quantum group, which lives in the product of the equivariant cohomology of the all quiver varieties. So by construction, both these objects act on quiver varieties. And like you should think maybe about this Yangian in the following way. So the quantum multiplication by divisor is determined by the Lie algebra. And if I want to consider higher Chern classes, I should look at something. So the corresponding quantum multiplication is governed not by the Lie algebra, but the Yangian. So, yeah. And so I should stress that the way this Yangian and also the Lie algebra are reconstructed goes essentially as follows. So what comes directly from geometry of quiver variety are the so-called R matrices, which are the essentially braidings of the category of representation of the Yangian. So this is a Yangian, meaning it's not only an algebra, but it's a bi-algebra. So the category of representation is a braided category, and studying intertwiners is essentially means that we are studying R matrices, so braidings of the category. And this comes from geometry. Of the quiver varieties. So I don't have much time to enter in the details, but the punchline is that there are certain. So if I'm given my quiver variety, I can pick some torus inside the EF, study the affix locus right here. And I want to study its cohomology and study maps to to my whole quiver variety. So I'm studying some kind of extension problem where I want to extend a class from the affix locus of my quiver variety to the whole quiver variety. And there are some canonical way of doing this called stable envelopes. Depending on some choices, as you see. And they are matrices, so the braiding of the category representations are given by the transition matrix between these stable envelopes. And if one picks the torus A wisely enough, then from the structure of the quiver variety, one can see that essentially one can really identify this operator with the braidings of the category of representations. I have to move to chapter 3, which is about the orderly algebra that we are considering today. Of course, interrupting if you have any questions. The BPS side. The BPS Lie algebra. So let's start once again with our picture of a quiver. So let's pick, for instance, A2. So, as I said, we can, whenever we are given a quiver, we can study the representation of the quiver for some dimension vector D. If I want to consider the cotangent boundary of this space of representation, well, the formal thing I can do is to double the quiver, meaning that whenever I'm given an arrow, I can introduce an arrow going in the opposite direction. So the space of representation of this quiver is theta QD. And let's call it, so let's say this is Q, then this is going to be Q bar, the double quiver. But I can do something even fancier. I can consider the double quiver and then add some extra arrows. I will denote this quiver by Q tilde. And
At each vertex, you add,
I add a single loop at each vertex. So, and if I'm in this context, then I might consider a representation of this triple quiver. But I also want to consider some kind of potential. This is the canonical cubic potential. It has the following form. So if I denote these loops by omega I, then my potential will be omega I, mu I, where these mu I are essentially the entries of my moment map. So I want to consider this kind of quiver with potential, and whenever I'm in this situation, I can consider the Jacobi algebra of such quiver. And so this gives rise to a Calabi-Yau category, and I might be interested in studying its DT theory. So from DT theory of the Jacobi algebra, I can cook up some categorified version of the DT invariants that go under the name of cohomological algebra. So this is critical cohomology, so cohomology with respect to the vanishing cycle of the trace of the potential. But if you don't like critical cohomology, then you can use the following result, which followed from dimensional reduction to Davison, that says that this is the same as the sum of the cohomologies of Boyle-Moore homologies, technically, of the zero loci of the moment map. So I'm trading the cohomology of a smooth space, but the critical cohomology with the cohomology of a singular space, where this is the moment map for the double quiver. some facts about the cohomological algebra. So first of all, it's an algebra. It's not only a vector space. So there's a multiplication. And this multiplication is given by so-called Hege correspondences, which is a fancy way of saying that essentially the multiplication encodes extensions of representations. So fact. First of all, my whole algebra is an algebra. As I said, any text on quiver varieties. And finally, I will put it in the form of a theorem, which is again by Davison. So which is here by the way. And so that there exists a generalized Moduli algebra such that the cohomological algebra is isomorphic as a vector space to the symmetric algebra of G BPS plus Q times the homology of the classifying space of BC star. So in other words, you should think this is some sort of PBW theorem for this so quantum group in a sense, if you like. This is some sort of analog of the Youngian introduced before, but actually it's only half of this Youngian, because as you see, it does not depend on the whole Lie algebra, but only on its positive part. And of course, there are many features that the authors studied about this BPS Lie algebra, so they have like a very precise description of the Cartan datum of this BPS Lie algebra in terms of the intersection and cohomology of the good moduli spaces attached to this guy, but I don't have time to discuss it. Instead, I want to discuss another fact, another theorem, which is again due to Davison, and so it's also from Lie, that says that if I pick greater dimensions of the root spaces of the Lie algebra, I recover the whole Katz polynomial. So I'm addressing one of the questions I raised before. So if I pick some root space of my BPS Lie algebra, and I consider the generating series of its cohomological dimensions. Cohomological dimension exists because everything comes from cohomology of those modular spaces. So I pick some cohomological degree I take the corresponding piece of the root space, and I cook up this generating series, then it turns out that this is exactly the whole Katz polynomial. So not only the degree 0 piece, but the whole of it. So essentially, as you can see, studying geometry of quiver varieties, studying modular spaces of representation, I can cook up two Lie algebras, the Maulik-Okounkov Lie algebra and the BPS Lie algebra, and they kind of address all these questions. So they are defined whenever we have loops. So there's no loops assumptions anyway here from section 2 onwards. In the BPS case, I do recover the Katz polynomial. using the BPS Lie algebra. So they come from enumerative geometry. So of course I've been very sketchy here, but hopefully I managed to convey the fact that Maulik-Okounkov Lie algebra is attached with Gromov-Witten theory of quiver varieties. BPS Lie algebra comes from DT theory of the Jacobi algebra. And so it remains to address the last question, so question number 4. So are these two Lie algebras any related? And so luckily, there's a nice answer to this question. By myself and Ben Davison. So there is a ZQ0 times Z graded isomorphism from the BPS Lie algebra and the Maulik-Okounkov Lie algebra. Modulo center. I will comment on it soon. And it intertwines the action on the cohomology of quiver varieties, the equivalent cohomology of quiver varieties. So saying that this is ZQ times Z graded means that it's as fine, so it's like the best possible isomorphism in a sense. So the root spaces are preserved and the cohomological degree is preserved. And it does what we would expect it to do, so it intertwines the action of quiver varieties. So that's where all this the algebra come from. And modulo center, what does it mean? So we'll explain it with an example. So if you take the Maulik-Okounkov, it's the BPS Lie algebra, let's say, of the AM-1 quiver. This is SLN. But if you take the Maulik-Okounkov, this is SLN plus a center, which is Q to the M-1. This is just the center commutes with everything, so you can like get rid of it and just compare the two together. So, right, exactly. So, well, obvious corollary, which is interesting, it's a conjecture proposed by Okounkov around 10 years ago, that says that the generating theory of the the dimension of the cohomological pieces of the algebra are equal to the Katz polynomials. So it follows from the previous theorem and the last year. And there's another corollary, which is well, important, at least for those people that like quantum groups. So there's at least one, which is me. So the positive part of the Maulik-Okounkov Yangian. So maybe it's right this way. So this Yangian has a triangular decomposition. So like the Lie algebra, we can take the positive part. Is isomorphic as an algebra to the cohomological algebra. So these are essentially the main results. But so I think that in the last 3 minutes I would like to, so of course interrupt me if you have questions, but otherwise.
Sorry, so the left hand side only is it true that the left hand side only involves a 2-point M02 bar for the Gromov-Witten?
The left, so you said?
Yeah, the Yangians, the Lagrangian correspondence is given by 2-point function. 2-point.
Yeah. So I think it's interesting to say a few words about the proof, which is, well, I would say a bit technical. No, but not only it is technical, but it's also conceptual. So we'll try to address, to explain at least how we can try to compare these words, which are like pretty different at least a priori. So, I get the theorem. There exists, this is again together with Davison, an isomorphism from the big cohomology of a quiver variety so let's say TF equivariant. Let's say C star bar H bar I can do better, but I would overcomplicate the notation. So to the Bauer and Mu homology. Let's say QF. So this Bauer-Mu homology is some piece of the homological algebra for the frame quiver, okay? And there is an isomorphism whose image is a piece of the BPS Lie algebra living inside of this guy. So the idea is that we can. So the idea is the following. So what is the cohomology of quiver variety? So, or what is a quiver variety? So a quiver variety is the zero locus of some moment map for the frame quiver. But I need to put some stability condition. So the stability condition is generic, so I can take semi-stable or stable locus, it's the same. And quotient by GD. So here, instead, I have no stability condition at all. So this is a stack, if you like. The brackets. And I have an open embedding here. And the idea, so the way you should think of this map is as an extension map. So it's something that picks a class in the cohomology of quiver variety and it extends to the whole stack of representation. So it's relatively close to, I would say it's close to what Daniel explained yesterday evening. And so it is inspired by the work of Maulik and Okounkov, where they call it non-abelian stable envelope. So yeah, I guess my time is up, but let me just say in 2 seconds that the idea is that as soon as you have such an identification, you can act here by the BPS Lie algebra of the unframed quiver, essentially. You can act here by the Maulik-Okounkov Lie algebra, and so this map provides a bridge to compare these two words. And another thing, so this is called abelian stable envelope, but do not confuse it with the stable envelope that I defined over there, which is kind of the abelian version that is used to define the Maulik-Okounkov Lie. Anyway, this is the end.
Any questions?
Yeah, regarding the second corollary where you compare the two algebras, like, does it follow formally from the comparison of the Lie algebras? Because it seems you like the cohomology and the
Yeah. The idea is that as soon as you know that it is called the Lie algebra, and so you know also another fact that essentially this is. So you can first define a map. You know that with respect to the Lie algebras that live inside of these spaces, then you know that these spaces are generated by Lie algebra and topological classes together, and since this map preserves action by tautological classes, you deduce the isomorphism.
So I have a question. So how specific this quiver case is? Because I mean, for the right-hand side, you can consider some other Calabi-Yau two category, like Higgs bundle, for example, of a curve.
I mean that's right. So I mean, and found the quiver case essentially models some of these other Calabi-Yau categories. So, like, I don't know to what extent we can push this kind of arguments. So, of course,
but the cohomological invariants are more global.
Right. So there's no Maulik-Okounkov side for that story, but I don't know, maybe trying to translate some ingredients, we can learn something. So, but the punchline is that I don't know. So,
there's no concrete conjecture which express the right-hand side, like for the Higgs bundle case, in terms of the quantum cohomology of Hitching moduli spaces.
I don't have one to give you.
So if I put a hat on your examples on the left-hand side, do I just put hat on the right-hand side? Like AN, BPS work, then AN quiver using SLN.
Yeah, hat.
Hat.
Yeah.
Just GL,
Yeah.
So what is the second one? What is the Maulik-Okounkov?
There is a morphic. So that's essentially this theorem. So
I'm just wondering about the abelian part. What happens to the abelian?
To this abelian piece?
Yeah.
So this abelian is exactly Q to the number of vertices of the quiver. So nothing changes. It's always finite dimensional. So the story is that more or less, if you have so this the abelian, so the Cartan, let's say, part of the Lie algebra can act on a quiver varieties by some eigenvalues in two ways. So eigenvalues that are function of f and eigenvalues that are function of d. So that somehow this is the reason why it's twice as big as you would expect. You can act by functions in f and d. But f is preserved. So but the f part is always preserved by the rest of the Lie algebra.
How do you get a map from Yangian, like in second Ferrari again? I think it's related to Changi's solution. Like, how do we get a map from one side to the other?
So what we do is that we show that everything is embedded here. So for a sufficiently enough torus, everything is embedded here.
So you can recover.
So we can first, so we know that, so that's also how we compare the Lie algebras after all. So we have this psi, and essentially this psi will allow us to compare the image of the action of the Maulik-Okounkov Lie algebra on the cohomology of quiver variety and the image of the action of the BPS Lie algebra on the cohomology of quiver variety. And then we show that they are the same. And then if you essentially, from this fact together, that the fact that everything is generated by the Lie algebras and the action of tautological classes here, you deduce the state.
And what do you mean by positive parts of Yangian? Like, do you suggest there is some triangular decomposition?
Yeah, because there's a triangular decomposition of it's a decomposition just as vector spaces, not? I mean, and this is going to be a subalgebra as well, but. So this is effectively the part of the Yangian that is generated by the positive part of the Maulik-Okounkov Lie algebra, so GMO plus, and again the option of topological classes.
Yeah, so it's not really a triangular decomposition of the Yangian effects.
Not as a bi-algebra.
For the main theorem, you don't have the hypothesis that there are no loops.
No. I mean, I assume. So in the first section, I avoided considering quivers with loops simply because I wanted to discuss Nakajima's and original results and the Katz constant conjecture. In that case, I think it's better to avoid loops. But yeah, from section 2 onward, in particular, all the main results that they propose here allow any number of loops. And actually, depending on the amount of loops you have at a node of a quiver, the resulting Lie algebra will highly change. I mean, the idea is that if you can consider this at the following quiver. So let's say that on, I don't know, some edges here, I don't care. But I have no loops here, one loop here, and multiple loops here. And I look at the Cartan matrix of the. So here I will have a 2 in the diagonal part. Here I will have a 0, and here we'll have something negative. Will be like -2. So if G is the number of loops, G -1, I guess. No, -2, G -1. So it's going to be negative, and so somehow you should think of this Lie algebra as something generated by some SL2 triples, but at the end of the day, what this SL2 triple behave as you're used to, really as SL2 triples only on when the diagonal piece of when they are attached to some vertex whose entry in the Cartan matrix is positive. If this is 0, they behave like some kind of Heisenberg algebra. So like you have E, H, F, and H is going to be central if it corresponds to a vertex whose entry in the Cartan matrix is 0. If instead you have the negative entry here, so the corresponding, you might have many E's here associated to a single vertex with multiple loops, and so in that case you don't have the cell relations, which is somehow what control the algebra. So you want to get it. So for instance, in a quiver like this, the positive part is going to be a free Lie algebra. It's something quite different from what you are used to in the case of Moduli algebra.
So is there a non-abelian version of this story where instead of starting with the stack of representations of algebra, you start with some representation of a reductive group?
So if you replace this G with something with something that is not a product of GLN.
Yeah, and a different vector space, and you take like.
Yeah, I don't know. I think in general you don't even have the Coha structures. So on the Coha side, you don't have the.
It wouldn't be an algebra.
Right. Yeah. I'm not sure what it would be, but I think it would be interesting to think about.
Okay, so if there's no further question, let's thank the speaker again.